Hello students, welcome all. So let us start today's session. If you remember last class we have discussed about binding energy, average binding energy, packing fraction and all that, right? So today we are going to start with the important graph of binding energy per nucleon versus mass number, right? That's the graph of average binding energy, average binding energy versus mass number A. So how does this graph look like? Average binding energy means binding energy per nucleon versus mass number. So this graph looks like initially it may be going a little bit high and then it goes to a peak value and then it attains like a maximum. So this maximum happens for iron Fe, and of course here it is for hydrogen, then helium and other things. So you can refer to NCRT. This is iron 2656 and here helium 24. This is hydrogen, or you can say deuteron. So we should know from this graph, of course this is 56 here and there are values going like this. So what is important point to note here, that this is having maxima at this point iron and the minima is for deuteron. So note here the values. So minimum binding energy per nucleon or average binding energy minimum is nearly 1.11 million electron volt, and this is for deuteron. This is hydrogen isotope, and maximum binding energy average is 8.75 million electron volt for iron. Okay, so what is the importance of this? What is the importance of this graph that we have to understand? Because this graph indicates the stability, and which nucleus has maximum stability, because this graph is showing average binding energy, and average binding energy gives the the binding force, or you can say nuclear force, right? Per nucleon, how much individual nucleon is inside the nucleus bound up, and if this is very high means it is strongly bound within the nucleus by that nuclear force, and it is very much stable. So if you see that minimum value is this deuteron and maximum value is for iron. So iron is like the maximum means it's most stable. So here we need to note that the reactions that happen, the nuclear reactions, two kind of nuclear reactions happen. In one reactions, a small nuclei combine to form a bigger nuclei, and in another type of reaction, which is like the fission reaction, where a bigger nuclei and unstable nuclei split into smaller nuclei, right? So the idea is that if you try to see from this graph, the nuclei this side, smaller nuclei, will try to combine to form a bigger nuclei, and similarly this side, which is the bigger nuclei, will try to break down into smaller nuclei, and they will tend to come towards iron because iron is most stable. So note that this process is called fission, nuclear fission, and this is called fusion. So fusion reactions are happening in the stars where hydrogen is combining to form helium and so on. So where they try to get more stability, they try to achieve more binding energy per nucleon, right? So this graph is very important in NCERT also given, and many questions have already come, and that sometimes they check that whether this reaction is spontaneous or not. So for checking that, you need to see whether these reactions are coming towards iron, and if there are energy released or not. That we will see later separately, like exoalgic and endoalgic reaction. But this is important point. This graph, and there are many important things to note in this graph. So let us make a note of important points from this graph. And this value we have to remember that, right? We need to remember these values. So let us make some notes from this graph. Note. Point number one, that binding energy average is higher for mass number between 30 and 170. So from this graph, everything I have not shown here, so I am writing these important points, that average binding energy is higher between this range of mass. And if you go mass number greater than 170, there is some pattern to be observed, that beyond this, binding energy per nucleon or average binding energy decreases up to 7.6 million electron volt for uranium. Okay, and in this point you need to note that minimum binding energy average is minimum for odd number of protons and neutrons, like lithium 36, boron 510, nitrogen 714. For these three, the binding energy, I am seeing the trend only for this case. Remember, this trend we are seeing for and means mass number greater than 170. And this is the trend here that we need to look. Another point to note here, that this binding energy average is maximum for even number of protons and neutrons, like helium, carbon, oxygen. So we are talking of mass number greater than 170. No, I think this point we have to keep separate point now, because this is trained for that. These mass numbers are smaller, right? This is for smaller. this ma- this odd and even rule we have to note in general. Binding energy minimum and binding energy maximum for odd number, for even number. Why it is like that? Because if there are even numbers of nucleons, even numbers of protons, even number of neutrons, there is nuclear forces are symmetrically effective, and there is, more attraction. They are more stable. But if it is odd, that means nuclear forces are not quite balanced, so they are unstable. You can say that, right? Okay, so I think this effect is for smaller values, for a less than 30, less than 30 it is. Okay, this idea is for less than this. What about if it is greater than? That means higher side, higher side. That also we have to note. For a greater than 240, they are distinctly nuclei are distinctly unstable, and these nuclei undergo nuclear fission reactions. So if there is a nuclei of 240 mass number, it can break down the smaller nuclei of nearly same 120 mass numbers. That can happen. Nuclear fission can happen. Similarly, point number 5, we can add that lighter nuclei combine for more stability. Example, you take hydrogen can combine to form helium. This is fission. So this is fission. This is sorry, this is fission, and this is fusion. Already in the graph, I have explained that we need to note. Okay. So that's the important point that we need to learn here. That fusion happen for a reason. The reason is to attain more stability. Right. Now let us go into the different types of nuclear reactions like exoergic, endoergic. What are the characteristic features of that? We'll write some reactions and we will try to calculate the Q value, how to calculate Q value, and how it is also related with energy. That we will see, and then we'll move forward. Right. So let us note about exoergic reaction. Exoergic reaction. Suppose in a reaction A plus B gives C plus D plus some Q. So this heat is released, right? This heat is released. And how to, and note that these are called reactants, and these are the product. So heat is released means some mass is getting destroyed. Definitely, we are considering some destruction of mass because mass is converted into energy. So this side mass must be larger than this side. So we can calculate this delta m mass change that is happening is mass of A plus mass of B minus mass of C plus mass of B. This is how, and delta m is definitely positive. We are considering mass changes. So this side mass is more, this side mass is less. So this Q value, we can calculate Q value as delta m into C square or delta m into 931.5 million electron volt by C square. Delta m in atomic mass unit we can use, right? So this way we can solve portions. I think C square we don't have to put, this will come in this million electron volt. Okay. Then how do we also calculate this? Q values are also related with kinetic energy. Note that the same Q value can be related as kinetic energy of products C plus kinetic energy of D minus kinetic energy of A plus kinetic energy of D. If they have given kinetic energy, we can also calculate Q value from this equation as well. Okay, right. But here, note very important thing that this Q value can also be calculated in terms of binding energy. So it is binding energy of C plus binding energy of D minus binding energy of A plus binding energy of B. Again, here Q is going to be positive because Q is heat released. Heat released Q has to be positive. Like this, we are going to calculate Q value. So this idea we should not get confused. Q is heat we are calculating, but heat release or heat absorbed that we can decide. Very small technique is there to understand. Because this side the reactant is going to form product and heat is released means finally they are more stable. Product is more stable means the binding energy of product must be larger. Common sense it is. We should not have any confusion in that. Okay. Then endoergic reaction. Endoergic reaction. Heat will be absorbed here. So if I write A plus B, so some heat will be absorbed and then it will become C plus D. You may write Q this side also, but you have to write then as negative. But I am writing Q as positive because heat is absorbed here. Absorbed. Heat is getting absorbed. Okay. So, yes, Sam, some network problem was there. Oh. Mhm. Why? What happened? Okay, no problem. Let us continue. So, endoergic reaction. Today we'll try to wind up this chapter. Few things are there. Let us cover that. So, endoergic reaction means A plus B and Q will be heat absorbed and C plus D. So, here we should note that the mass of A plus B is going to be smaller than mass of C plus D because energy is this side. This energy is in a way you can say it is a mass because energy and mass are same, equivalent. So right side mass is larger, left side mass is smaller. So mass of A plus mass of B, right? This side mass is smaller than mass of C plus mass of B. So if you want to calculate mass defect delta M, we need to write that side mass C plus mass of D. That side mass we have to subtract from this side mass A plus mass of D. Okay. This is how we'll calculate, and the Q value which is required is delta M into C square. This heat is absorbed, and again we can write this as delta M in atomic mass unit or multiply with 931.5 million electron volt. This we can write. Then also note that we want to write in terms of binding energy. So this key value can also be written as binding energy of A plus binding energy of B minus binding energy of C plus binding energy of So this time we have to write binding energy left side product minus reactant minus product, because these reactants are more stable. So they are not forming just like that. You have to give energy to make it unstable basically. So C and D are obviously unstable, but you have to give energy to convert into that. This is where people are confusing. They are not understanding what they are doing calculations. So exergic, endoergic, this is the main thing you need to understand. And of course, binding energy can be converted into average binding energy into the number of nucleons. Those calculations we can do. Right? So this is about the reaction endoergic and exergic reaction. So any nuclear reactions that happens, some conservation principles are followed. Any nuclear reaction, any nuclear reactions, any nuclear reactions following conservation principles are followed. Principles are followed. What are those principles? First, mass, conservation of mass. Second, conservation of energy. Third, conservation of charge. Fourth, conservation of linear momentum. Five, conservation of angular momentum. Right? These are the five. These are the five principles. Right? Then what else? Now we are going to discuss about the nuclear force, some of the properties. So we have discussed about the nuclear reactions which are happening, and nuclear reactions are happening because nucleus want to get more stability, and in that process it is losing some mass. That mass is getting converted into energy. That is the binding energy. Binding energy means the nucleons are bound inside the nucleus by some kind of force. That is what is nuclear force. Let us study about the nuclear forces. Okay. So some of the features of nuclear forces we need to study. Features of nuclear forces. What are some of the important features of nuclear forces? So first thing is that nuclear force nuclear force is the strongest in nature. In nature, nuclear force is the strongest force. So if you compare gravitational force with electrostatic force with nuclear force, you will see that this ratio is nearly 1 is to 10 to the power 36 is to 10 to the power 38. So nuclear forces are among the strongest force in nature. Second, nuclear force, the short range force. Nuclear force is a short range force, short range, because it acts within the nucleus. So if you consider uh, distance distance between nucleons, distance between nucleons, if distance between nucleons is greater than 2 femtometers, nuclear force becomes negligible. That means the distance should be within that. So the range of nuclear force is nearly, so nuclear force is maximum for distance nearly 1.5 femtometer. For 2 femtometer, that means after 1.5 femtometer, the nuclear forces between nucleons start decreasing, and at 2 femtometer it becomes negligible. Beyond 2 femtometer it becomes zero. That means nuclear force act within a small distance, right? That is what it is. Short range. The next point to be noted is nuclear force. Nuclear forces are basically strong attractive force, but it contains a small component of repulsive force. Repulsive force. This will become clear if we see this diagram. Potential energy in million electron volt versus R. So this is the point where potential energy is minimum. R no. Minimum potential energy. And just before this minimum potential energy, we have, and this R naught is nearly 0.8 femtometer. So before this we have repulsive forces. That means for this side we have repulsion, and for greater than this we have attraction. Okay, and this attraction remains up to what? Up to 1.5 femtometer. Right. After that it fades away. So this is an important point to note, that nuclear force remains active, but it is also made of repulsion, because if you go beyond below smaller distance, smaller than 0.8 femtometer, then nuclear force can become repulsive also, and from 0.8 to 1.5 femtometer it is attractive. Okay, like this. Wherever potential energy minimum, this force is almost zero. So before this forces will be negative. Why? Because if you remember, force is given as minus du by dr. You remember that? So if the slope is positive, force will be negative, and negative force means attraction. So you can see that here slope of the graph is positive. So the force will be negative. Negative means attraction. This side the slope of the graph is negative. Negative into negative will become positive. So that's why this side repulsion is there. And this is the point where it is force is zero. Total force or nuclear force is zero. So nuclear force start acting from this attractive nuclear force starts acting from 0.8 up to 1.5, up to 1.5. Then this is a rough diagram. Note that this you may say that here also slope is becoming zero. No, this is not that slope is becoming zero. Here, of course, as I told, it is like a maximum. So this graph you need to carefully understand. Like a potential energy graph, slope is maximum of this graph. Okay, slope of the potential energy is maximum. That's the idea. After that, up to 2, it become almost 0. You can say that 1.5, it is almost like a maximum. After that, it's suddenly starts decreasing, and then it may decrease and it may become, or it may become like a constant. Okay, so this graph is a rough graph. We need to understand because there are experimentations and uh, performed, but this graph is a approximate theoretical graph. Slope is here maximum. Maximum slope is happening here. That is what we have to note. Maximum slope. Because if slope is maximum, then this will be minus minimum. Minus means more attractive force will be there. Okay. Okay, next point. Let us go to the next point. Point number 4. Nuclear forces are saturated. Saturated force. What is saturated force means? A nucleon experience nuclear force only due to its neighboring nucleons. That means only the neighboring nucleons affected. For example, suppose this is a nucleon and it has neighboring nucleons this. So these will only affect it. Other nucleon, these nucleons will not be affecting it. Okay. So this nucleon will get affected only due to its surrounding. This one, this one, this one, this one. These only can affect this nucleon. Other nucleon which are away from it, they will not affect it. That is why it is called saturated. Saturated means it only depends on the nearby nucleons. Then another point to note that nuclear forces are charge independent. Point number 5. Nuclear forces are charge independent. That means nuclear forces acting between neutron is same as nuclear forces acting proton is same as nuclear force acting between uh, proton neutron. Okay, nuclear force does not depend on the charge. Now, what very important point is that net force between, let us calculate net force between neutron. This is going to be same as net force between neutron proton. But the net force between proton because proton has some repulsion between them, so attractive forces decreases. That's why this is going to happen. This we need to note. We are talking about the net force. Net force means net nuclear force, resultant force which involves the total forces. So this is net attractive force we are talking about. Net attractive force. Why the net attractive force between proton is smaller? Because they have same nuclear force, but because of repulsion, electrostatic repulsion is happening. So resultant nuclear force of attraction decreases. But between proton neutron there is no charge because neutron doesn't have charge. So electrostatic repulsion is not there. Between neutron also not there. Only between proton repulsive nature is coming because of electrostatic force. Okay, that's one point. Then next point number 7. Nuclear forces are spin dependent. Spin dependent. Spin dependent means the nucleons. Suppose you take this nucleon and this nucleon. Suppose these nucleons are having parallel spins. Parallel spin means like this angular momentum or spin angular momentum. So if they are parallel, then they have greater force between them, right? So there is greater nuclear force. They have parallel spins. Parallel spins. Parallel spin means greater force. But if suppose the nucleons are having anti-parallel, one is like this way, another is like this way. So anti-parallel spins means they have smaller nuclear force. Both are attraction only, but nuclear force will be smaller attraction and larger attraction. It depends on this spin. So next point number 8. Nuclear forces are exchange forces, and then okay. So note what are exchange forces. So inside the nucleus, proton are getting attracted, neutron getting attracted, neutron proton are getting attracted. So how are they getting attracted? There is a question. So scientists have made some theory that these two nucleons, they are exchanging, they are playing with each other. Suppose two boys are there and there is a uh, two balls, they are having two balls. Okay, one boy has one ball, another boy has another ball, and each of them are throwing balls towards each other. So they are busy in catching that. So that person throws, that person also throws, he will catch, he will again one, he catch, he throw again. Like that, they keep on playing, they are playing the game. So inside the nucleus, these nucleons are playing the game, right? So there are smaller particles called meson. What is that? That's what they are exchanging. So proton will exchange with each other pi naught. Neutron will exchange pi naught, and uh, proton and neutron they will exchange, right? So neutron will send pi minus, and this is pi plus. Doesn't matter. You write this way or that way. Okay. So proton will give pi plus and pi. So what is this pi? Pi naught, pi 0, pi minus. These are called mesons. They are called mesons. So mesons are also further small particles which are being exchanged between the nucleons inside the nucleus, and by exchanging these, they are bound together. The two boys are exchanging some ball between them, they will be bound together because he cannot go anywhere, he has to catch it. He is now bound with that. So that kind of a theory is there. They are called exchange forces. And last one is non-central. Last point, nuclear forces are non-central. Nuclear forces are non-central. Unlike unlike gravitation and electrostatic. Unlike gravitation and electrostatics, they are non-central. What does that mean? So central means central forces, central forces means the force which act along the line joining the centers, along the line joining the centers. But non-central means they can act in any direction. There is not much known about these non-central forces. Okay, so that's what that much we should know. Okay, so after this topic, we are going into radioactivity. In radioactivity, there are alpha decay, beta decay, gamma decay, right? And after that, we can go for nuclear reaction, nuclear reactor. That will be the last topic. Then we will be winding up. Okay. So let us go into the radioactivity. Law of radioactivity is of course not there, but in the syllabus I think it is there. So quickly we'll cover that. Radioactivity. What is radioactivity? Let us write down. Spontaneous decay, spontaneous decay of an unstable nucleus by the emission of certain particles like alpha particle, beta particle, and gamma radiations, gamma radiation, and gamma radiation to attain stability. This process is called radioactivity. So radioactivity means a bigger nuclei will decay into smaller nuclei. Okay. So let us say, for example, that there is a nuclei which is X, which we represent as A set. This can become a smaller nuclei. Uh, Let us say this become A dash Z dash, and it will be emitting certain particles like alpha or beta or gamma. Gamma, of course, is radiation. Gamma will come. So alpha, beta, gamma, all this, and the smaller nuclei will come. So what will be that nuclei? We can calculate that. So let us now go into this modes of decay. Different three modes of decays are there. Modes of decay. So first we will take, there are three modes of decay: alpha decay, second beta decay, third gamma decay. So let us study one by one. So what happens in alpha decay? Alpha decay, a nucleus Az will break into A minus 4 Z minus 2 and it will become alpha. Alpha means this is what is called alpha particle. Now in alpha particle it is very important to know about the formula for energies and these things. Okay. Also one point to note here, that this point let us note it. Radioactive decay is not affected by external condition of temperature, pressure, etc. Because this is a nuclear reaction, it doesn't get affected by temperature, pressure. Okay, so in alpha decay we want to find out that, let us take alpha decay happens and this is one nuclei and it is going to break down into another nuclei, and this is alpha. So let us say that initially it was at rest. This is x, this is y, this is alpha. Because the total momentum conservation has to take place, so this will go with the same momentum which it will go, both will have same momentum because they need to cancel out, momentum conservation will happen. Remember its mass is a, its mass is a minus 4 and this mass is 4, but of course this is 2, this is e minus, sorry, z minus 2 z. So anyway, atomic number is not important, mass number we are going to write. So let us write the kinetic energies. Kinetic energy ratio, kinetic energy of y by kinetic energy of alpha. Kinetic energy is p square by 2m. Mass means mass number we will write. Here also p square by 2, mass means mass number. That become 4 by a minus 4. So kinetic energy of y becomes 4 by a minus 4 times kinetic energy of alpha. This is one equation we are getting. Second thing we should note that the Q value, because in these reactions some energy also is released, okay, we know that. So this Q value is kinetic energy of y plus kinetic energy of alpha minus kinetic energy of x. But x is at rest initially, so this is only kinetic energy of y. And y kinetic energy, let us substitute 4 by a minus 4 times kinetic energy of alpha plus kinetic energy of alpha, and this is anyway 0. This is what is Q. So from here we are going to calculate kinetic energy alpha. You take common, then you will find it is a by a minus 4, right? Because when you take LCM, minus 4 plus 4 will get cancelled. So from here kinetic energy of alpha can be calculated as a minus 4 by a times Q value. Q value can be calculated by the mass, delta mc square we can use to calculate, right? And also note that we can also now calculate kinetic energy of y. Kinetic energy of y can also be calculated now, the daughter nuclei. When you substitute this, a minus 4 will get cancelled. So 4 by a into the Q value. This formula we must remember. We must remember this. This will come in calculations. Okay. Then beta decay. Let us go into the beta decay topic. Second is beta decay. So there are three ways beta decay happen. There is beta minus decay, there is beta plus decay, and the third is called electron capture. Electron capture. So let us take one by one. First we'll take beta minus decay. Beta minus decay is nothing but it's an electron. Electron is coming out. So let us take nuclear reaction. So remember the nucleus, it will become, mass number will remain same, but z will become plus 1 because electron is minus 1 0 almost. Okay, So if you take it like this, then it will get, and suppose some energy is also coming out. This is what is happens. Beta minus decay. This I have written beta minus decay. Then what is beta plus decay? Beta plus decay means x is z. Mass number doesn't happens, but this will become like this, plus 10 plus. But now I think we need to also note that some other kind of particles are also coming out. These are called anti-neutrino. I think I should write it, otherwise confusion will happen. Energy is of course there, but let me write about the particles. This particle is called anti-neutrino. Very important, and NCERT it is given. Anti-neutrino, and this side it is called neutrino. Neutrino. Okay. Anti-neutrino, anti-neutrino, anti-neutrino. These are also some kind of particles. Some kind of particles it is. Okay, but here note important thing in beta minus and beta plus decay. There is an important point to note. What is that important point? That in this kind of a reaction, beta minus decay, the electrons means what is actually happening, the n by p ratio, neutron is to proton ratio decreases. This ratio decreases. Okay, n by p ratio decreases. But in this case, beta plus decay, n by p ratio increases. Okay, this is what we have to know. And actually, why it happens? Because in this kind of reaction, beta minus decay, neutron is breaking down into this proton plus electron, electron minus plus this antineutrino. But in case of beta plus decay, a proton is breaking into a neutron plus a positron plus neutrino. So this is the mechanism. You can say this is the mechanism happening. This is the mechanism in beta minus decay and beta plus decay. Okay. So neutron is decreasing into protons, and by p ratio decreases. Here neutron is increasing, proton is decreasing, so n by p ratio increases. So this kind of reaction happens for that reason only. If n by p ratio is large, so n by p ratio has to become small. So that's why beta minus decay will happen. And if n by p ratio is small, then beta plus decay will happen, so that n by p ratio increases. That's the logic behind it. Okay, they will ask questions that why beta minus decay happens. If they can answer assertion region based question. Okay, so this we need to remember. And then the third mode that we should note is electron capture. Sorry. Electron capture. Electron capture is third. So there are some parent. First, let us note a reaction. Electron will capture, and Z minus 1 will come. Then positron will come, plus neutron will come, and heat will be released. Okay. So here you can see that this is similar to beta plus decay. This you know, similar to beta plus decay. So what happens? Sometimes a nucleus will capture its own electron. A nucleus becomes so unstable that its own electron, outermost orbit, that means the nearest orbit, that is, let us say first orbit electron, it will capture. So if it captures that electron, That electron goes inside the nucleus, and this is the nuclear reaction happening. Okay, that's how nuclear reaction is happening. So electron is capturing, it is becoming this, right? And there is a anti-neutrino. I think neutrino, that is neutrino. Okay. Then done. What else is remaining? Gamma decay. Last is gamma decay. So these are all beta decay only. Now let us go into the gamma decay. Gamma decay is the third kind of decay. Gamma decay. In gamma decay, no changes happens. So we should know that gamma rays are electromagnetic waves with wavelength lambda less than 0.1 nanometer. So these are nothing but the photons which are coming out. So suppose Xaz is there will be no change in this, but photons are coming out. Photons. These photons are gamma rays. Why the photons are coming out? Because inside the nucleus there is some transition happening. This is like a metastable state to ground state. They are called isomers. You know that. Beginning we have discussed that. Different type of nucleus. So the state is changing. Like for example, inside the nucleus, we believe that inside the nucleus also the nucleons are present in different energy level, and as this nucleus comes, these photons are coming out. These photons. These are what is gamma rays. That's all. So I think we are done with that. Then properties alpha, beta, gamma, these are not very important. Then law of radioactivity is there. Law of radioactivity, and after that nuclear fusion. Law of radioactivity quickly will wind up. Maximum 5 minutes will take to wind up that. Law of radioactivity. So have you studied chemical kinetics? Because this topic is related with chemical kinetics. Have you studied that? It is decaying with some alpha, beta, or gamma, all these things are happening. So let us say at time equal to 0. This number, we are talking of the parent number, parent nuclei. This is daughter nucleus. Parent nucleus, daughter nucleus. So at time 0, number of parent nuclei is equal to n naught. And at time equal to t in general, this number of parent nuclei is, let us say, n. And note that it is decreasing because it is decay happens. So the rate of decay, which is dn by dt, is proportional to n, but it is a minus because it is decreasing, its number is decreasing. So when you remove the proportionality, dn by dt becomes equal to minus lambda n. This lambda is called decay constant. Decay constant. So now let us integrate. So from here we bring dn by n is equal to minus lambda dt. Let us integrate initial n naught to this n, 0 to t. When you integrate, this will come ln n by n naught is equal to minus lambda t. So time can also be written as 1 by lambda ln n naught by n. First of all, this is the formula for time which we can remember. Time formula. Also, we want to derive that, so n is equal to n naught e per power minus lambda. This is the number of parent nuclei as a function of time. This is called decay graph, and not decay like this. Okay. So the idea that there are two important times is defined. One is called average or mean time, other is called half-life time. So from this graph we can try to understand that. If you see this graph, suppose number becomes n naught by 2 at some time t. So this time t will be calling as t half, right? And after some time n become n naught by e. N naught by is further this side. This is n naught by e. This time that will call tau. Okay. So there are two times here, t half. When time become t half, number will become half. And when t become tau, which is called average or mean time, number becomes n naught by e. So substitute here in this time formula 1 by lambda ln n naught by 2. So that become, this become t half. This is called t half. So t half is 1 by lambda ln 2. Similarly, if I substitute this tau 1 by lambda ln n naught by e, that becomes 1 here, so 1 by lambda. So tau is 1 by lambda. So we should remember that. Okay. And also we should remember that, let us say that initially it is n naught. After one half life become n naught by 2 power 1. After two half life it is n naught by 2 per power 2. After next half life it will become n naught by 2 per power 3. Like that it will continue. So after x half lives, number will be n naught into 2 power x. After x number of half life. Okay, so this is what we have to note. And also note that what is the number decade, because this n refers to number of remaining. Number decade is equal to original number minus n. So n naught minus n naught e to power minus lambda t, and naught can be taken common 1 minus e to power minus lambda t. That's what it is. So similarly, we have a term called activity. Activity is nothing but the rate of decay. That is called activity, which we are going to write as R, which is dn by dt. So if you calculate R, dn is minus, sorry, uh, what is dn? And we already know, and not equal power minus lambda t. I think we need to put a minus sign because this rate is negative. Let us do this calculation. Minus comes out n naught e per power minus lambda t, and 1 minus lambda also comes. So from here this rate is lambda n naught e per power minus lambda t. And if I put time 0, then this become r naught. So this term is called r naught. So rate is equal to r naught e per power minus lambda t. Rate of decay. So rate of decay also follows the same law as this number follows. It is going from R naught to like this. Exponential decay happens. For both the rate as well as this, the same type of graph it is. Okay, okay, so now here important thing is the unit. Sometimes there is asking the unit, they may ask the unit of decay, unit of activity, let us note. The units of activity is 1 becquerel is called 1 decay per second. 1 decay per second, that is called 1 becquerel, and this is the SI unit. This is 1 becquerel is SI unit. But beside this, there are many practical units. What are those practical units? 1 Rutherford RD is 10 to the power 6 becquerel, and 1 Curie is 3.7 into 10 to the power 6, 10 to the power 10 becquerel. These units we should remember. And there are two types of radioactive decay can happen. One is called series, another is called parallel. Parallel. What happens in series is that suppose X decays into Y will decay into Z, Z may decay further like this. And in case of parallel, X will decay parallelly into Y and Z. So these kind of patterns happen. Okay, series and parallel decay, and there are some specific, ways how do we calculate that. Okay, so if a nucleus can decay simultaneously by so many processes, that is what is parallel decay. Okay, and series decay. So these are also possible here. I think these we can take up also afterwards. So parallel decay, remember here, suppose if element is decaying into, let us say this is lambda 1 and lambda 2, these are the decay constant here. So effective decay constant lambda effective can be written as lambda 1 plus lambda 2. Like that, in parallel we have to add it like this. Okay, and in half-life calculations and other things are done in the same way. But in this case, suppose this is lambda 1 and lambda 2. So here effective case is written like this. No, that is for this only. Okay. Here also there will be some method that we will see that. But for parallel, mostly parallels are coming. So 1 by tau is also 1 by tau 1 plus 1 by tau 2, and 1 by t half effective is 1 by t half 1 plus 1 by t half. Okay, these formulas are also used for parallel. For series it will be more difficult. Series it is more difficult, calculation happens. Okay, but let me write the formula for this series. Series formula also let us write. So in series, suppose I write like this way: A is going into B, and B is further disintegrating into C, and so on. And suppose this is lambda of A and lambda of B. So here we can write this formula. This can be derived, but I am just writing it here in order to skip more calculations. This is the derived result which require a lot of calculations, but I am just writing it, okay, to do it fast. Okay, this is how the number of B can be calculated at any time. Number of B can be calculated like this. Okay, so more calculations are there, but let us not go into more details about it. So that is not there in slides. Okay, that's also this is over. This topic of radioactive decay is over. More detail can be given in advanced class. In advanced class, they can ask. But right now, this much only we have to know. Okay. Let us go into the nuclear reactor and this nuclear fusion process. We will see quickly. Okay. So nuclear fission. What happens in nuclear fission? So first of all, we should know that in this uranium 235 92 is bombarded with a neutron, right? A neutron is bombarded and it can convert into barium 141 56 plus krypton 9236 plus 3 extra neutrons comes out, and there is energy of 200 million electron volt. This we must remember, they will not give in the question. Okay, so what happens that this neutron is going to bombard in this nucleus, and one neutron is producing three neutrons. Okay, a heavy nucleus is split into almost equal parts. They are, okay? Large amount of energy is released. Sometimes they may break into some other thing, barium krypton. Instead of barium krypton, they may break into some other nucleus also. That is also possible. Okay. So what is very important to note here that there are called two type of neutrons. Neutrons released or neutrons produced. There are two types of neutrons produced. One are called prompt neutrons. Other is called delayed neutrons. Delayed neutrons. More than 99% of neutrons produced in this fission process are prompt. This is more than 99%. So these three neutrons which are produced, 99% are prompt, means fast moving. Okay, prompt means fast, or you can say they are immediately produced. Delayed means they are taking some time to come out. Okay, that's what it is. They are produced within produced within 10 to the power minus 18 to 10 to the power minus 15 seconds. Very fastly it is produced, and they are almost 1%, and they are delayed. That's why the name is called. Okay, they take time. They are produced over a period of time. And these are the delayed, which are very important for nuclear reactors or nuclear reactions. Okay, and what we need to note here, a few important points, that delta m mass defect or change of mass is nearly 0.214 atomic mass unit is happening, and this is the first point to note. Second point is 0.1% of mass of reactants is converted into energy. How much percent? 0.1% mass. We can calculate this also. From here Q value is 0.214, atomic mass in it 931.5. You will get this nearly 200 million electron volt. This is how 200 million electron volt is calculated. This is per fission reaction. In one fission reaction, this much energy will be released. Right? Now we need to understand the chain reaction, very important topic of chain reaction. Okay. Chain reaction. So we know this uranium is bombarded with one neutron, and this is producing barium, and it is producing krypton, but it is also producing three extra neutrons. These extra neutrons can again bombard another three uranium nucleus. And if this happen, then again barium krypton will be produced, but again these three neutrons are getting produced, right? So the number of neutrons are getting multiplied geometrically, and if let us say they are allowed further to have bombarding with another three uranium nucleus, then they will produce lot of immediately they will produce, because this is happening at a very high rate, exponentially it is happening. So lot of energy will be produced. That is what happens in a uh, atom bomb. Okay. The process of continuation of nuclear fission, which once started, continues spontaneously without supply of additional neutron from outside. So we don't need to supply extra neutron, because one neutrons once bombardment happen, these neutrons keep on producing, and these neutrons keep on further doing nuclear reactions with further uranium nucleus. So this is called chain reaction. Kind of chain reaction will start. Okay, now here chain reaction we can control it also. To control it, what we will do it, we need two things. Okay, chain reaction can be controlled, first we need to, by slowing down neutrons we have to slow down, and second we need to also absorb neutrons by absorbing neutrons, right? So that's what, for slowing down we use, I think we use moderators, moderators, and for absorbing we need cadmium rods, cadmium rods or boron rods. Boron rods, cadmium rods are used for absorbing neutrons, and moderators are graphite, water, or heavy water. These are the things which are used as moderators. Okay, definitely we can control them. Now, one important point we need to note is reproduction factor. Reproduction factor. Okay. This reproduction factor K is defined as number of neutrons in the in next generation by number of neutron in previous generation. Okay. So if three cases are there, K is less than 1, second is K is equal to 1, third is K greater than 1. So K less than 1 is called subcritical state. K equal to 1 is called controlled state. Controlled state. K greater than 1 is called super critical state. And this is what happens in atom bomb. Controlled state means it happens in nuclear reactor. In nuclear reactor. Subcritical means you cannot have further reaction. So try to understand what it is. So this means, let us say in the next generation 3 neutrons are produced, and in the previous generation there is one in. So ratio 3:1, that will become 3. So this is what is going to happen. This is called supercritical state. In that, what will happen? More chain reaction will become uncontrolled. But suppose if you absorb 2 neutron, out of 3 neutron produced, 2 neutron you absorb. So every time you are absorbing 2 neutrons, so 1 neutron is only effectively getting used in each stage. So that is what it is controlled. But sub-controlled means, suppose 3 neutrons are produced and let us say you absorb all the 3, or the number of neutrons is becoming smaller. So that is what happens subcritical. In this way, it cannot sustain that chain reaction. Chain reaction cannot be sustained. So these are the 3 important states, right? Now also note here what is called critical critical size. Critical size is uh, the value of 1 by k. Critical size is the value of 1 by k. 1 by k value is called critical size. Okay. If the size of substance is even slightly less than the critical size, chain reaction will stop. If size of substance is even slightly less than critical size, the chain reaction will stop. Okay. So done. So this is what it is. Now we are going into nuclear reactor, and quickly we will write important points. So nuclear reactor, or it is also known as atomic pile. Atomic pile. So there are in nuclear reactor controlled chain reaction are carried out. Controlled chain reaction are carried out, and next produces nuclear power or energy. What are the essential components? Essential components are: first, fuel; second, moderator; third, control rods; fourth, coolant; fifth, radiation shield. Radiation shield. Let us quickly note about all this. So first we are talking about fuel. So in fuel we will use uranium 238, uranium 235, Pu 236, thorium 232. All these are the fuels used in nuclear reactors. Okay. Then next, Moderators. Moderators. Already we discussed moderators. What are those moderator purpose? Purpose is to slow down fast moving neutrons, to increase the rate of nuclear fission, because fast moving neutrons may not do nuclear fission reaction. So example, here we are already telling heavy water. What is heavy water? That is D2O. Second, graphite. Third, beryllium and beryllium oxide. They are also used as moderators. But note that heavy water is the best moderator. Heavy water is best among all. Okay, so let us go to the next controlling rods. Control rods. They will absorb neutrons. Absorb neutrons. So already we have given example cadmium, boron. Sometimes steel is also used. Steel rods are also used. Cadmium, boron, and steel rods are used. But out of all this, cadmium is the best. Best it is to absorb. What about the coolant? Coolants. In coolant, they use coolant means it will lower down the temperature. So we use air, CO2, carbon dioxide also use. Water is also used. Organic liquids are used. Helium is also used sometimes. Liquid sodium is also used. But liquid sodium is the best liquid coolant. Among the liquid coolant, it is the best. Then last is radiation shield. Radiation shield. What is radiation shield? To protect, right? So for that, what do we use? Concrete walls. Concrete walls of several feet thick, and lines with metals like lead. Lines of leads are there because lead can absorb harmful radiations. Okay. Then so last here is power calculations, which is very important. Power of nuclear reactor. Power of nuclear reactor is calculated as N by T into E. Here E is 200 million electron volt. N by T is number of fissions per second. Okay, so this directly will calculate, and note that 200 million electron volt is nearly 3.2 into 10 to the power minus 11 joule. But the power will be very high because N by T number of fusions are going to be very very large. Okay, n by 2. Suppose if you want to produce a power of 1 watt, suppose I want a power of 1 watt, so number n by t will be p by e. So 1 by 3.2 into 10 to the power minus 11, you calculate, we need 3.125 into 10 to the power 10 fusions per second. Very large number of fusions can happen per second. Okay, so this is what it is. I think we are done with this. Then lot of applications and other things you can study from the books. Then last topic is nuclear fusion. Nuclear fusion, let us discuss nuclear fusion. Nuclear fusions, two small lighter nuclei combine to form a bigger nuclei, but of course energy is needed here. Without energy you cannot fuse. So one of the most important example is hydrogen combining into helium in the stars, and we have this energy of 25.7 million electron volt. Again, this you have to remember. So this nuclear reaction fusion happens at very high temperature. At very high temperature, which is nearly 10 to the power 7 Kelvin, lighter nuclei combines to form heavier nucleus. Why this much temperature is needed? Because they need to overcome the repulsive force between the nucleus, right? And note that because they require lot of temperature, so they are called fusion reactions. Are called fusion reactions. Are also called thermo thermonuclear reactions. They are called thermonuclear reactions. Okay, so we need to remember all this fact. And fusion reaction happens, that is hydrogen bomb. Hydrogen bomb. So hydrogen bomb, in order to start hydrogen bomb, we need very large amount of energy, because to do fusion we need to give lot of temperature. For that we need to first do a fission reaction. That fission reaction will give energy, then fusion will happen. So this hydrogen bomb is nothing but a fission fusion bomb, or fission fusion reaction happens. So inside a hydrogen bomb there is a atom bomb also. So I think now we are done with the necessary things we have covered, but still there are many things theory which you can read NCRT book, particularly for need. But this much is sufficient for calculations. Okay, so we are winding up this chapter. Then the next last chapter which is remaining is semiconductors. That we will be going with the slides to cover up that fast. And in the few classes, that means one or two classes, we will be winding up that, and then we will be um, you know closing this NEEV, sorry, this TEJAS 1.0 program. We will be only continuing with test series, and only that revision series or crash course series will be going on, where we will be where I will be creating test papers and you will be writing tests, and we will be discussing the test portions only. Fine. So thank you all for attention. and let us continue further, keep working hard so that we can achieve our goals, right? Thank you all. Bye bye.